Again, is an honor to be here with you guys and also to talk about something that very I'm excited about and very close to my heart. So hopefully, through this talk, you will be able to at least get to know more about AI and also how can we actually use it in geosciences. And so today's talk will really about the emerging opportunities of AI in geoscience, and we'll discuss about the various challenges and also a way forward. How can we improve the utilization of AI in geoscience? Before I start, I would like to acknowledge all the collaborators. All the works that I will be showing you guys will not be possible without contribution of all these great scientists all around the world. As you can see, I cannot list all of them, but mostly this is what I could show you. And we have your own Ivan Ferreira, and he has been, he is a really great, I will say, very young researcher, and it's an honor to me to work with him in different projects related to AI in geosciences. So um, since I guess most of you are undergraduate, I finished my PhD back in 2019, but it feels like, it's not that long ago I actually finished my bachelor. So before I talk more about AI and, a little bit deep about AI, I would like to share a little bit about my academic and professional journey. So it all started in my home country in the other side of the world, the other part of the world, which is in Indonesia here, where I had a chance to work in different, projects during my final undergraduate project. For example, here I did some mapping for coal bed for coal bed methane exploration, and then from there I moved to Saudi Arabia for my master, working with carbonate rocks. And then during my master, I had a very, amazing opportunities where I could participate in this flugal course. If you are, working with carbonate, so you must know this. Flugal is one of the founding father of carbonates. And then I had also a very unique opportunity. As I mentioned, I did my master in Saudi Arabia, with a deserted, very hot area, right? But then during my master, I visited this area here, which is Svalbard. Svalbard is like the northmost uh, university in the world. And this I experienced like completely different environments, completely different geology, which again really give me a lot of insights about geology, what we have in the nature. And then from there, I moved to the UK to do my PhD in the University of Manchester. And for my research itself, I focus on this area here, which is the Western Canada Sedimentary Basin. I work with Cambrian carbonates. So as you can see, I've been working with quite many different subjects, right? And it's okay. It's completely okay to to switch from one subject to another subjects because at the end of the day, it really complement your knowledge and also make you a well-rounded geologist. One thing that I would like to say here is, I'm not sure if you can see it here, that you are really defined by the people around you, right? So it's that really who you met along the way, along your journeys, that will really define who you are and really shape you as a, as a scientist or as a geologist. Just like we zoom in about my academic professional journey, can be divided into two parts. I started my undergraduate back in 2007, and then from there I worked in for 1 year in ExxonMobil as a coal bed methane and deep water carbon exploration, working in the field and well site geologist. So again, it's completely different things that I did during my undergrad. And then for my MSc, I work with carbonate rocks also again here, but one thing that I would like to highlight, we were able to actually secure this IBA competition. I was part of this team, and we won the third prize globally. And then during that time also I had the opportunity to visit University of Miami, where I did some like geochemical analysis there. And then from there, I again went back to my home country. I work as in an oil company, back working in carbonate reservoir, mostly now looking at the fault, structural diagenesis, working as carbonate sedimentologist. My plan was to stay for quite some periods there, but then, we have the fate tells us different things, right? So then I got a PhD, a scholarship to do my PhD in University of Manchester. And again, during this time, I got the opportunity to spend some time in the University of Miami, University of Alberta, and also Research Institute in Glasgow. And from there, just a few months after I finished my PhD, I moved to Stanford. And this is where really my interest or my research about AI is like capitalized, right? So this is where I did a lot of all my research, because again, we have a very strong and healthy environment where you can do like cross interdisciplinary collaborations between different departments in computer science, electrical engineering, so on and so forth. And then right now, I'm I just newly joined this university in the College of Petroleum Engineering and Geoscience in Saudi Arabia, and I'm still an assistant professor. My research is mostly divided into two sort of end members. So one is working with carbonates, and the other one mostly focusing on the application of AI in geoscience. So just quickly, maybe to some of you, this is your first time to hear about KVPM. So where is KVPM? KVPM is located in Saudi Arabia. And as you know, this is the whole Saudi Arabia here, and it's located in the eastern part. The most eastern part of Saudi Arabia is very close to Qatar, UAE. Here, this is UAE, this is Oman, and also, and other neighboring countries. And what's really cool about KVPM or our university here is we are sitting on top directly this carbonate rocks. So the university or all the buildings is built on top of this Eocene, Oligocene carbonate rocks. And why I brought this to you, because the first oil discovery back in 1944, I will say, in Saudi Arabia, it's exactly, if you see this hill there, where people stand there, this is actually the hills. So our university is not that far from where they first discover oil in Saudi Arabia. And as you know, the rest is history, right? It really changed the course of history in Saudi Arabia once they found these huge oil resources in this area. So we are sitting exactly in what they call Dammam Dome. So it is like a big anticline, which mostly composed of carbonate rocks. And this is where they found the first discovery. So our university is pretty green. Yes, outside we have a lot of dunes, deserted area, but our university is pretty green, pretty nice. In the night, as you can see from my background. And this is some quick facts and figures. We are really focused on petroleum engineering and geosciences, and we are currently 7 in the world based on this ranking. So that's a little bit about my journey and also where I am now, and hopefully you get a better sense about my background. So let's move to AI. So what's exactly AI? I mean, as you know, most of you have mentioned almost all the right words. So let's try to divide it into two different things, right? So we have human. We tend to learn from experience. That's us, right? As we grow from as a baby, and then childhood and adult, we learn from experience by seeing many different things, by hearing many different things, and from there we can start recognizing objects. And the other spectrum is completely opposite. We have robots, right? Robots is just designed to follow instructions. So there is no intelligence in robots, right? You need to program the robots. You need to tell exactly what it needs, or what they need to do. And from there, they will just be able to follow the instruction as you give from the programming. So AI tried to combine these two worlds, right? we want to have a system that can learn from experience, but in the same time without explicitly program, right? So this is where you start introducing intelligence into your system. It means your system will be able to make their own decision, right? By looking at different, or in our case, by learning from experience, or from a more layman terminologies, by looking at different data sets, right? And then from here, we can, build a system that have some sort of intelligence that can learn from experience, and then later on make all the predictions and do all the automations, right? So that's really the really basic things about AI. So I think one of you also mentioned about Turing, and this is exactly where it all started, right? Maybe you also even watched the movies, right? Where Alan Turing created these machines, or what they call now Turing machines, where it can start learning from patterns, right? And this all back in 1950s. And then after that, we have different development of AI algorithms, and one thing is very notable is the perceptron. And perceptron is sort of the first algorithms that try to replicate how our human brain works. And then from there, this is where we have the first golden age of AI, where we have a huge booming of AI everywhere. People start exploring, developing different, algorithms, architectures. And then after that, in 1975, this is where backpropagation, which is the building block of what artificial neural network we have today, right? So it all started with this backpropagation. But then the problem comes here, right? This is where they have the first AI winter, and what they realize is actually they don't have the technology yet to fully support these algorithms, right? So it's totally underpowered. And from there, again, technology start to develop, and they start thinking neural networks are really cool. Again, the way it learns, the way it actually make predictions, it's something that very close to us, like human brain. But then it reached a point where, again, we have the second AI winter, where neural networks are underpowered again, because the technology just wasn't there. It's not ready yet for this kind of algorithms. And then from there, different algorithms have been developed. Maybe you have heard about like support vector machines, like random forest, decision trees, and this is what we call today as traditional or conventional machine learning algorithms. And then later in 2010, we have the rise of the machines, or GPU, right? And this GPU allows you to have a very efficient, distributed computing that really helps neural networks to rise again from the ashes, right? So then nowadays, this is what we have today. It's just a big booming of application of AI everywhere, right? We have in almost many different aspects in our life, you will find AI everywhere. But one thing that we need to keep in mind, this is not a new field, right? So every time you hear about AI, again, even the architecture that we are using right now, for example, like the one that's really powerful for image analysis, which is convolutional neural network, is all developed back in 1980s. But again, the technology wasn't there. So then today we can start using it. Right? So this is not a new field. So you need to be also very wise or very considerate when you look into like different studies or publications, right? Because yes, there are also new studies that actually developing new algorithms, but at the same time, some people, they ride into this big wave, right? So they just use a very old algorithm and try to apply it. I mean, it's fine. I mean, it can work, but it's not really something that we are looking nowadays, right? We are looking for a more complex algorithm that can help us solve complex problem. As I mentioned, we have AI everywhere. You can just name it in many different aspects, even from like, businesses, education, finance, healthcare, government, even gaming. One thing that's quite interesting is in the automobiles. where they try to create the self-driving cars, right? And this is where all major developments of AI have been focusing on, right? Because the self-driving cars is really a game-changing technology, right? So all of efforts, all of the brilliant minds are getting together to use AI or to solve these complex issues with AI. So where is geoscience here? Just wait, and I will show you in a couple of slides where we actually use AI in geoscience. So then how to use AI? Okay, AI, it's a very general term. AI is an umbrella of all this terminology that we hear today, like machine learning, deep learning. We have artificial intelligence that engulfing all this terminology, right? So AI, as I mentioned, is computers with the ability to reason as humans, right? So it has this intelligence, learning from experience without explicitly programmed. And within AI, we have the subset. Okay, so machine learning is part of AI. It's not two completely different subjects, right? So machine learning is actually, now we are talking about the actual system, right? That can learn about, learn the algorithm that can learn without being programmed. And then from there, we have even a smaller subset, what we call today deep learning. And deep learning is a, combination of networks that's capable of adapting itself to new data. And as you can see, sometimes we use this terminology interchangeably, right? But it's actually, these all three are quite a different terminologies. So again, you need to be careful when you try to use these terminologies in your day-to-day life. So this is quite interesting cartoon, which I think is quite applicable to what we have today, right? So typically, this is the way we look at how we can use machine learning, or AI. Some people will say, okay, we have this machine learning system, and you just try to pour this big pile of data, and also just apply different algorithms, and then the main question is, what if the answers are wrong? Then our job, you just stir the pile until they start looking right. Or it means in our case, we're just tweaking the algorithms, fine-tuning the parameters until it looks right, and until the results make sense to us. So this is in the past we have this issue even until today, but we are definitely improving from this issue. But in the same time, there is no rule of thumb when you try to apply AI. There is no like neural networks are the best, or the more data the better for your model. Sometimes yes, sometimes not always the case, right? Neural networks sometimes can give you like 95, 99% accuracy, but in some cases you just need to have like a simple regression to solve the problem, right? So you want to make sure you know what you are looking for, how your data looks like, how your data structure, before you go even using or applying AI. So then it's important to clearly define and understand the problem you are trying to solve. And here, this is very important in geoscience, which is domain expertise is a key, right? Because in our case, in geoscience problem, you cannot just give your data to computer scientists or computer engineers, right? They know how to create these algorithms, but they don't know how our data looks like, how the relationship between the data. So this is where you really comes from, right? You have your geological background, geological knowledge, and you combine it with machine learning expertise. Then from there, we can actually start thinking about how can we use AI in geoscience. I would like to bring this to your attention because again, when you talk about general people, especially like big companies, this is what they typically think about when you mention about AI, right? They will say that yes, you have data and put into this black box, which is AI, and then you get the value, right? But in the actual world, it's actually you have the data, and inside your data, you have many different things you need to do. The same in the AI itself, you have data engineering, you have the modeling, and this is probably one of the most important part. You need to do data exploration, data cleaning, right? Normalizing, feature engineering, so on and so forth. And then from there, you get the value. And even once you have your value or prediction, then you have some constraints, right? Maybe you have some legal constraint, maybe you have some ethical constraint, historical or security constraints, right? So this is again something that you always need to keep in mind, right? You cannot just using like a brute force apply AI everywhere and just try AI sort of randomly to get a some predictions for your data. And why this data engineering is very important, because again we need to remember that AI is just almost like a blank page, right? It has it knows nothing basically, right? It only learns from what you teach them, right? So for example, if you give AI a bunch of cat images, then AI can only recognize a cat, right? You cannot ask other pets or other animals to be recognized if that's your data is only contains cats. So the same here, right? You need to be very mindful that what is your data, what are you trying to predict, and what is you're trying to test, right? Because this all needs to be in one big harmony, right? Otherwise, you pretty much just wasting your time try to apply AI to your data. So again, try to just make it very clear here. You have your data. This is always start with your data, right? And from your data, you try to construct your data set. Typically, you have raw data, then you need to do many different things to make it, your data set ready for machine learning. And from there, you go to train and evaluate and then model deployment, right? Once you satisfy with the results, then you can deploy your model. But one thing you need to remember, data is what mostly your time will be spent on, right? It's 70 to 80%. This is all about getting your data right for machine learning. And we know that we have this, tendency that we just want to jump directly and try to apply, because AI is cool today. Like every time you talk about AI machine learning, people will get very excited, very interested, right? But then I will ask you to step back a little bit and just think carefully about your data, and you need to really spend time there, right? Because once you solve it, like once you make your data clean, nice for machine learning, and just to create a model, train the model, and deploy it, it's only taking into like 1/5 or maybe 20% of your time, right? And once you have your data ready, then you can do many different things with machine learning, right? Because otherwise, you need to go always back and forth, without actually getting the right results, right? And again, we use AI to optimize our time, to make time efficient analysis. But if you do it wrong, then you actually, wasting your time here, and you make everything not efficient anymore. So I guess that's very general things about AI. And now let's move into artificial intelligence and geoscience, right? And why we are interested to see and to look how can we use AI in geoscience here. Just quick articles here about emerging opportunities for AI in geoscience. Mostly, we are dealing at least with these 5 big problems, right? Lack of access to the latest technical knowledge, right? For example, most of this technical knowledge are clustered in the big companies or big, let's say, oil companies and big academia institution, right? And in between, we are pretty much quite lost, right? And then also we have this lack of experience, right, inside. So because when you try to start analyzing geological data set or geological problems, you really need to have very in-depth experience or in-depth knowledge about that particular area. For example, you cannot just ask me, I know some of you guys here is from the economic geologists, right? I almost know nothing about economic geology, so I cannot just, although I already got my PhD, I cannot just jump do all this, try to apply AI in economic geology because I don't have the background, right? And this is also quite a very common problem that we have, which is oversimplification of problems, right? As we know, geology is very complex, so we try to oversimplify, right? And that's where we start to introduce some error or bias there. At the same time, we have too much data, but not enough analysis. Like, for example, if you think about oil exploration or mineral exploration, within one day you can actually generate thousands of data set, but then most of these data set will just stored somewhere, nowhere. Nobody will touch it again. So this is where AI comes from, right? Let's see what we can see or what we can use this data, this huge amount of data, and we try to use AI to find patterns, optimize some of the analysis, and also make some predictions. And this is quite an interesting article published in Science, I would say, or Nature, I believe, where they use artificial intelligence to find surprising patterns in Earth biological mass extinctions, right? So again, as you can see here, there is a huge potential of applying AI. You just need to do it the right way and find the right problem to apply. So where can we apply? What kind of data set? There are many different things, many different kind of data sets, but for this talk, I will just focus on computer vision. Computer vision is one branch of artificial intelligence, and when it's focused on image analysis. And why I chose this one, because as we know, in geology, we are dealing with multi-scale image data set, right? You have from remote sensing, we have from basin scale seismic images, up to a micro scale petrographic or thin section images. And this is all images with different attributes, with very interesting features. And these really provide us with very unique opportunity to apply AI in geoscience, right? So, and the reason why we are interested in looking at these different scales of data set, because this is the way as geologists build our model, right? We try to integrate, we try to combine many of these different information, and we try to use the, like the salient features, right? The important features of these different data set or different images to create a diagram or a cartoon or a model that represent the actual world condition, right? And this is why computer vision or image analysis has very huge potential to be applied in geoscience. Then the next thing we need to do is, we can just put machine learning on it and see, right? And we have all the data sets there, we have all the problems there. Now our job is try to see where and how we can use machine learning on it. So before I go into detail, let's look into the early days of AI for computer vision, right? Again, computer vision is nothing new. This is all goes back to 70s, 80s. And in the past, the way we teach computer to recognize an object in a single image, is by telling the computer with with a set of mathematical algorithms that, for example, a cat has these pointy ears, right, with chubby body, with long tails, and from there, the machine will be able to, the algorithm will be able to recognize that, with this feature, it should be part of, or belong to a cat. The same with geological object, right? For example, we have this rounded circular grain, which is very distinctive. We call it UIT, right? And we can tell UIT, if you want to use computer vision, that UIT has this different layering with nucleus in the center, right? And from there, the machine will be able to recognize that this is an UIT. So we have this machine vision, we call it computer vision. We can use a traditional machine learning, traditional algorithm, and also nowadays we try to apply deep learning. What's really the motivation behind moving or switching from traditional machine learning to deep learning? Because as you know, if we take a cat as our example, cat can have many different shapes, right? For example, it can be in the very funny way, a contorted shape like this. It means you need to introduce new set of algorithms or a set of rules, right? Your previous rules doesn't work anymore. And then, and as we know, there is almost infinite number of possibilities cat can appear in an image. For example, if you have a very low contrast between the background and the actual cat itself, but sometimes, with this funny pose like this. So it's become inefficient, right? It's not efficient anymore because you need to keep introducing more and more set of rules. While in our main goal is actually try to develop algorithms to be able to recognize cat as a group, as a whole group, right? So you don't need to keep adding more and more features. And the same with OIDs, right? OIDs can appear in many different shapes or form. Sometimes you have different shape like this, can be heavily fractured and also dissolved, right? But we want the machine, or we want the computer or the algorithm to be able to still recognize this as an OID, right? We don't want to, keep adding features or keep introducing new set of rules every time we see different OIDs. And then, because as we know, we have these thousands of possibilities how OID can appear in an image. So this is one of the motivation why we want to use deep learning. And before that, just want to quickly show you that like how does exactly computer see an image, right? For example, we have an example here of one of the president in the United States, Abraham Lincoln. And if you see, machine doesn't recognize your image as a whole image, right? As a different shape of face and features in the face, but it's actually looking into different pixels, right? These different pixels, for example, is we are dealing with grayscale image, and these different pixels tells you about the colors contrast, right? And these different pixels, they have a specific number, and machine learning or deep learning use this number as their input, right? They read your image as just as a numbers, right? They don't actually see what in it, like what's in your image, right? So this is something you need to keep in mind. And the great thing about machine learning is, it actually takes each individual pixel as your data set, right? So if you imagine, if you have like a grayscale, normal grayscale with like 256 by 256, you end up with 10,000 data points already, right? And this is where we need deep learning, deep neural networks, because if you use traditional machine learning algorithms, then they cannot handle it, right? Because you're dealing with thousands of data points, millions sometimes of data points. And one thing is quite interesting, again, this all started back in 2010. And in 2015, this is where machine learning, or now let me switch it to deep learning, start to gain more attraction, or gain some attention, because it start to surpassing human accuracy or human error, right? It has error rate lower than human. And why human can have this error rate? Because human get tired, right, through time. And also once you're tired, then you start to introducing some error there. And at the same time, we have we can easily access like high performance computer, like a very high-end GPUs, and combining all this, it really help us to use deep neural networks or deep learning to do image analysis. But the main thing of why we want to use deep neural networks is because, if we see how our human brain and vision system works, so we see something, we see an object from, first we see it in our eyes, and then from our eyes we transfer this information through our brain, and in our brains we have these millions of neurons, and then it will be all processed, right, based on what we have learned from our past experience. And then from there we can recognize this object as a cat. That's how human learns, right? Or how human recognize an object. And even when you only get this part of a whole object or part of a cat, you can still recognize it, right? That's what really amazing about human. We don't need to have the whole picture. Once we learn about this particular object, just by looking at a tiny part of this object, you can start differentiating, or you can start recognizing this object. And this is exactly why they use deep neural networks. And deep neural networks is inspired by this human brains, right? Where we have different layers. We have input layers, which is act as our human eyes. And then from there, we transfer this knowledge into these millions of neurons, right? Millions of neurons inside of this deep neural network. And at the end, you create the prediction, right? You get the output. And then from there, one thing is quite interesting. Again, we learn, or deep neural network learns sort of hierarchically, right? So it looks into different features, from low-level features until high-level features. Looking at the pattern of local features and the actual object until it combines everything and recognizes the whole object. And this is exactly the same. Again, back to how human learns, right? We learn hierarchically, right? So we want to have a system that can understand and also know what we are looking at in the image, right? Otherwise, again, model just look into your image as a number, right? So we want to make sure we have a system, an algorithm that have the ability to know and understand what's in your image. So just a quick summary here between traditional machine learning and deep learning. With classical machine learning, you have the input image, and then you need to do this different feature engineering. And then you have your classifier algorithm, and you have the output. While in deep learning, this is all an end-to-end system, right? So there is no feature engineering here. This is all done within the network itself. So just again, another summary: if you have a seismic data, if you are using classical machine learning, that you need to do all this big feature extraction and engineering to look into the specific features. But for deep learning, you create these different feature extraction processes throughout your networks. So I will show you a couple of different study cases and examples or works that I've been doing. But before we move into that, I will just quickly introduce you in image analysis, especially the supervised learning for image analysis. In deep learning, we have three different categories, right? We have classification, where you try to identify cat, for example, here. So you just try to identify a single object in your image. And we have object detection, where you try to identify or locate multiple objects simultaneously. And also you have semantic segmentation, right? Where you can draw a polygon or a mask that exactly capture the morphology of your object. Because with object detection, you can only draw a rectangular box. And as you can see, different tasks here, it corresponds to different geological problems. So you need to, again, make sure you know what you want to use it for, and then from there you can try to see which one is more suitable for your data set or your problem. So this is, we try to apply it for petrography analysis. And from here, as you can see, this is like a study that we did during my postdoc, where we tried to analyze different carbonate components, like carbonate rocks components under thin section. And here, this is the classification accuracy between experienced geologists, geologists with limited experience, and deep learning. Yes, deep learning has a lower accuracy than experienced geologists, as expected. But one thing that really, great about deep learning, and what really deep learning offers here, is the combination between accuracy and speed, right? So the classification rate, as you can see, deep learning can reach five order of magnitude faster than human, right? It means in 1 second, deep learning can analyze 10,000 images, right? More or less 10,000 images with this very consistent accuracy, right? So if you imagine, if I ask you to analyze 10,000 images, maybe it will take you, a few months. And again, once you are tired, then you start introducing error there, right? And this is where exactly we want to use machine learning for. And beside that, we realized that it's actually not really applicable. We don't really, as a geologist, you don't really see this object individually, right? Instead we use it simultaneously at the same time, and this is why we try to apply this object detection in a real-time petrography. Here, for example, you can see we apply this technology, and just imagine if we can apply this technology and put it into your microscope camera, right? Then once you start your analysis, you can already start seeing different components recognized or identified there. So you don't need to have such a high expertise to start analyzing carbonate rocks, right? Otherwise, you need to call someone that experienced in carbonate rocks to give some description of your rocks, right? So again, by applying machine learning, not only it becomes more time efficient and optimize the problem, but also it helps geology more accessible to a wider community, right? That's our end goal there. So this study already published back in 2020. So if you're interested, just let me know. I'll be more than happy to share it with you. Another thing that we are also trying to do is we try to identify the lithology, or doing the lithofacious analysis. From here, we use image segmentation, and from image segmentation, you can get the proportion of different grains, and you can calculate each proportion between grains, matrix, porosity, for example, and then you can get the predicted or the classification in a more timely fashion. And then if by having this very time efficient analysis, then we can also start thinking about doing a more advanced analysis, integrating this with petrophysical properties, for example, thermal conductivity, so on and so forth. Another thing you can do, we move from thin section to a higher scale, which is a lower scale, if you like, which is the core images, right? And here we try to differentiate between bitumen-rich lithology and shale. And this is from hyperspectral data, and this is from deep learning segmentation analysis. As you can see, yes, it's not perfect, but it's quite close. Again, for the first screening, I think it's really a great tool to use. And for example, if you're interested with fossil analysis, we can also use this for bioturbation or trace fossil identification. And then, trace fossil can give us some information about the depositional environment and where these rocks deposited. So many works have been done. This is not really my area of expertise, but so many works have been done in seismic interpretation. There are so many things, for example, like geobody tracking, looking at channel bodies, fault detections, and many other things, right? And also some people focus on the more like the seismic facies analysis, right? Try to divide based on different formation, based on different horizon features there. So that's just like sort of the application of AI in geoscience. It's sort of direct application. So now, can we use AI to actually help answer bigger geological problems, right? So as you know, I'm sure you have heard about this terminology that present is the key to the past, right? But now the question is, can this be applied to carbonate system? Why it's important to us? Because as you know, the animals that we have today is very different than the animals were present at that 600 million years, 500 million years ago. So it means the information that we have in the present may not be applicable to the past, right? And this is what happened throughout Earth history. You have some changes in the animal evolution, you have mass extinction, so on and so forth. So the problem, have we been looking into the wrong place actually, right? So now let's look into this problem, and we have an example. We look into this Uit grain again. Uit grain is very unique and significant carbonate sand. Why it's very unique? Because as you can see, this is modern Uit with this feature, Triassic Uit, which is 250 million years ago, and Proterozoic Uit. They somehow share very similar, features and structures, but at the same time, they can actually very different, right? The way they form. And the good thing about Uit, they record their own growth history, which record in the same time the paleoenvironmental, seawater chemistry, so on and so forth. And maybe you have seen it, this variation in the ocean mineralogy is also derived actually from ooid mineralogy. So again, ooid is very important for us to understand how our Earth evolved through time. And one thing that is quite interesting is the ooid size. Again, ooid size is directly reflected the environmental condition where they form. So now, how best to measure ooid size? We can use manual conventional image segmentation, but as you can see, just a quick example, this is a very simple coin, right? We can use different segmentation method, right? But then from there, we have problems. Sometimes you cannot segment it, perfectly, right? You still have these problems, and in this case, you cannot really measure the size of each individual coins. And the same with ooids, right? If you try to apply this with ooids, because ooids can have many different forms, then you can have also this issue. So now how about if we apply AI or machine learning here? So we use this sort of a unit architecture here, and from there we can segment it, this individual ooid grains and get the size distribution. So then from there we get the first ever record of detailed ooid grain size across the Phanerozoic, right, for 500 million years ago until today. And this is the first ever record, and this really where machine learning makes something impossible possible, right? Because if you try to do it all this manually, then it takes years, right, to do all this manually, but also accurately. So once we got this size distribution, so we try to apply different statistical modeling, try to see how they form, try to quantitatively assess the parameters associated with the formation of ooids. As you can see, we have different sizes of ooid across different time scale, and we can see exactly the corresponding parameters there. And the same here, we test the sensitivity of ooid size. So then once you have all this trend, then the question is, can we use this to constrain ancient climate and ocean chemistry? And the simple answer is yes. And as you can see, we have, for example, different formation of giant ooids. Giant ooid means ooids are very large, more than 2 millimeters. And it's exactly matched with our simulation, right? So our grain size measurement and the condition they form exactly match as the prediction from our simulation. For example, here in the Cambrian and in the Triassic, where you have explosion of marine animals and also mass extinction, this is where you can create very huge ooids grain there. Okay. And again, this is already published, so feel free to reach out to me if you're interested. So just quickly to discuss about the future directions for AI in geoscience. As you can see, we have a huge appearance of publications from 10, 20 years ago until today. It increased up to like 10, 20 folds. So now how the future actually looks like. So we have this hype cycle, what they call it, from Gartner's hype cycle. So the problem we have today is costly dataset. The dataset is very costly to acquire. The labeling is very difficult, and also uncertainty, right? So now the question is, where are we now, right? Are we here in the peak of expectation, where we just try to apply machine learning everywhere, or we already passed through the trough of disillusionment, right? Where we start realizing, okay, the actual power of AI is in particular aspects of geoscience. If you ask me personally, I hope that we are here. We already passed this trough, but it seems we are probably still also here, right? Because you will just see our literature is flooded with AI application in many different things, and then when we reach this part here, then we are in trouble, right? So we have this slope of enlightenment, which I hope that we could arrive to this part soon, very soon, and then from there we can really see the actual potential of AI in geoscience. So if we keep doing what we are doing now, I think our future is not looking that promising, not that bright. This pretty much will just reach the plateau very easily. rapidly. But if we develop a benchmark data set, big data set, and very minimum labeling, then we can definitely improve, the application of AI. And then if we add explainability, right? So we get rid of the uncertainty in our model, then it will help again to actually realize or unravel the actual potential of AI in geoscience. So again, this is mostly my personal opinion. I think we need to develop a benchmark data set. This is what have been people developing in the other side, which is in computer science, where they have this ImageNet consists of millions of data set. So in geoscience, when you look at it, we actually have many different resources, right? But there is no place that actually gather all this data set. We have very, isolated data set. So it still take some time and, big expertise to actually start analyzing this data. So will we have it soon? I don't know, but that's my hope. If we have it, I think it will really open the, the new horizon in AI research in geoscience. Another thing that we could do is, again, we try to overcome the data limitation, limited data problems, right? This is where we can use synthetic data generation using what they call GANs, generative adversarial network. For example, this is an OIT again. If I just ask you quickly, can you differentiate between real and synthetic images here? And maybe some of you will, recognize it correctly, and some of you actually made some mistake. And this is, as you can see, some of this synthetic, real. So some of the synthetic looks quite real, and some of the real image actually looks quite, quite bad, which means it looks like almost like synthetic data set. So this is quite interesting. And once you can do this, it means you can generate almost unlimited data set, right? And it's already labeled, right? Because this all comes from a specific group. And this is one very interesting work that Ivan and myself have been working on, where we try to generate label-free, realistic synthetic petrographic data set, right? And we have a very good success here. And Ivan really did amazing work in this study. And we also even asked, did some survey here, and where, as you can see, maybe some of you also answered this survey, then mostly we got, incorrect answers, right? So it means so many people cannot differentiate between real and synthetic, and also mostly it's indistinguishable, which is great for us, right? It means even human, we cannot differentiate it, then it will be very helpful for the machine to use it as a data set. So coming into the explainability, as we can see here, we have the common trade-off between interpretability and accuracy. So as you go towards a more complex model, which is neural networks, then you start to decrease the interpretability, right? You decrease the explainability. Why? Because neural networks can handle nonlinear relationship, right? And this become very difficult to explain, and even us, we don't know exactly how the machine or how the algorithm make their decision. And this is the problem that we have today. When you don't have the explainability there, it means it's very difficult for us to put our trust, right, to invest in this technology. So then how do we make neural network more explainable? Again, things to remind ourselves that deep learning, as powerful as it is, it's very easy to trick. And this is a real example where deep learning sometimes cannot differentiate between blueberry muffin and chihuahua, and also, I don't know, bagel with dog, fried chicken with Labrador, so on and so forth, right? And even this is a very well-known examples where the machine actually say that they are 99.99% certain this is a magpie. But can you see any magpie here? I don't think so, right? And maybe you can see some patterns, but it's not that clear to us. Okay. So sometimes the way the machine learns is not really understandable to us, doesn't mean it's wrong, right? So we just need to explore more to really see or to really explain how the machine learns. One thing we can do is we can look at the uncertainty in this image classification, for example. So we have a different uncertainty, which is what they call aleatoric uncertainty and epistemic uncertainty. And this is related to either your model or your data set. And by analyzing the uncertainty, that means you have a better idea how the algorithm make their decision. And this is very important for you to further develop your model and also to exactly come up with the right algorithm to be deployed later on. So let's talk about the future of geologists in an AI world. I think it's only a question of time, but again, I still a true believer that AI will not be able to fully replace geologists. Yes, they can help us in make it our analysis more time efficient, optimized, but still domain expertise is something that we have, right? And we just need to integrate this knowledge to with machine learning. So then what is a must skill to have for future geoscientists, right? We are now in the new era of geoscience. So I will say, having a statistics, coding, machine learning, or data science skills, is very good for your future. Doesn't mean you need to use it for machine learning, right? You can use this knowledge or these skills just to be very critical, right? How you analyze your data. So you got sort of new insights, or you can come up with new insight how you analyze your data, because as you know, geology typically is very qualitative analysis, right? So by doing this, you can start introducing quantitative aspect of analysis in your geological data set. One thing is not really related to this talk today, but what I think is quite important is you need to have sort of this law making and also management skills, right? Because we need to start putting ourselves in the decision making process, right? In the past we typically just focus on our expertise, but then we forgot about these aspects that really backfire into us, right? So we need to diversify our skills in general. That's what I'm trying to say. So to wrap up, just my 2 cents here. Domain expertise is definitely always a key to apply AI in geoscience, because our field is very unique. Unlike, for example, in self-driving cars, right? When you try to label, cars, humans, animals, trees, you can just ask anyone to label it. But for a geological dataset, it needs to be a geologist, expert in geology, that can label the dataset correctly, right? So there is always a big need in domain expertise when we start talking about AI in geosciences. So deep learning has a great potential, definitely, to optimize geological image analysis with time efficient, cost effective, and also can provide with high accuracy analysis. For me, the future of AI in geoscience looks very exciting and promising if we do it right. Right? Again, we need to be very mindful of what we are doing, because the potential benefits of artificial intelligence are huge. So are the dangers, right? So we don't want to recklessly apply machine learning everywhere, right? Then once we can do all this in the right manner, carefully, then I think there are almost unlimited potential where we can start talking about or applying AI in geoscience. So that's all. I mean, if you are interested to know more about my research or KVPN, feel free to reach out here in my email. You can ask Ivan for my email address. I'm always happy to have a discussion with you guys. I'm in my group. We are always looking for motivated and talented students to join our group. So feel free to reach out. And that's all. I'm happy to take any questions from your side. Thank you.
Thanks a lot, Ardi. That was a great talk and a great introductory talk for this Road to Geohackathon that we're having in October. So I will ask the public if you have any questions to ask, to please share them. I will give them the ability to unmute yourselves, so you can speak now. And if you want me to translate the question, please write it in Spanish in the chat, and I will be more than happy to ask the question for you.
you have any questions coming?
I think Jose.
Sí. Okay, can you hear me?
Yes, yeah, go ahead.
Okay, as you said, the more important phase of solving problems with AI is dealing with the data engineering. But in this order of ideas, we need data to at least think to use AI algorithms. And we know how difficult it is to access to the data, considering the relevance and the cost of acquiring it by the industry. My question is, could you share with us some useful and free data sources and that we can use to reach data sets related to geoscience, like, I don't know, petrographic image, geochemical data, or even with log data?
Yeah, sure. Yeah, sure. That's a great question, Jose. I think yes, that's completely true. That data set is still main problems or main hurdle in geoscience, right? Because most of the data set is owned by a company and it's mostly confidential. So if I could go back here. So as you can see here, for example, all the things that I've uploaded. So for example, for petrographic images, you have this carbonate world if you're looking for a specific carbonate petrography. And we have also many different resources for like igneous thin section or many different thin section, right? For example, here from British Geological Survey, they also uploaded their collections of petrological thin section and also core samples. The same here from Norwegian Petroleum Directorate. They uploaded the well log data and core images. The same, if you're interested more about like remote sensing images, then we have Earth Engine public catalog from Google, right? So there are plenty, again, there are plenty of resources, but the only thing is there is no place that actually try to combine all this, right? And most of the data set, again, is not yet ready for machine learning, right? This is a very raw data set, so you need to do all type of data cleaning and so on and so forth before making it ready for machine learning. And I know, like, if you're interested in well log data, for example, like, I think like many geological survey, like Alberta Geological Survey, they release thousands of well data sets. The same in the US. I think from Kansas Geological Survey, you can find like 20,000 well data sets. So if this is something that you are interested, so then, I can direct you to the right resources. Thank you. Any further questions?
I think yes. If you can unmute yourself, Monica, or give me the question so I can ask it.
Yeah, go ahead.
The question is in the chat, so it is
Okay.
what publications are key to understanding this AI trend in geosciences. Also, she asks what we can do to eliminate the sometimes difficult and lengthy process of labeling data in geosciences. And another question, how can we create good machine learning models with limited data? So 3 questions.
Yeah, this is all again. Thank you. I think it's Maria, right? Yeah, thank
Maria.
you for your question. So, I mean, these all 3 are very important questions. So in terms of publications, I think mostly if you want to start, then you need to read about review paper, right? So I think there is a very good paper by Jasper Drums, where he summarized all the machine learning's application that have been going for the last maybe 50, 60 years in geoscience. So I guess that's a good place to start. If you need the actual paper, just send me an email and I could send it to you. But in the same time, AI is a very active field, right? It is actively growing. So then I will also encourage you to look for recent publications, right? Because if you read a publication published in 2020, there is a huge chance that the algorithm is already, outdated, right? It's not state of the art anymore. So the more or the recent papers you read, the better for your understanding. And then you combine it with this sort of big review paper about AI and geoscience. About your second question, what can we do to eliminate sometimes? In some cases, there is nothing we can do, right? You just need to label them, religiously, tediously, and because again, right, our data set is very unique, and it needs to be labeled properly for the machine to be able to start learn something, right? Learn the feature or learn something from your images. But also, just combining with your third questions, we have now different methods, right? The one that I presented to you is what they call supervised learning. It means you need to label the data. You need to tell exactly the machine what they need to learn on, okay? But in the other case, we also have unsupervised. Unsupervised, it means you don't need to label the data at all, right? So you just need to bring the data and let the machine to decide which one belongs to the same group. And they will come with the different groups. And then your job is to identify what the group means, right? And nowadays, we also even have what they call self-supervised. So it's almost like supervised, but then we teach the machine to learn everything by themselves, right? So with this all different advancement in technology, we try to reduce, right, our dependency with human labeling. Okay, so that's mostly my answer to your questions. In terms of limited data set, again, this happened not only in geoscience, in many different parts of many different scientific fields. So there are many algorithms right now that really trying to focus on how can we use limited data set, yeah, to apply machine learning. One method that's very well known now, what they call transfer learning, right? Because with transfer learning, it means you transfer the knowledge from one domain into your domain, right? So first you train your machine learning into the general domain. For example, like in this case, we have the ImageNet dataset. You train them there, and then you use their knowledge, or you transfer this knowledge into your domain dataset. And with this method, you actually can start using machine learning and getting good results even with limited dataset. So I guess, yeah, that's all. And we have another question from Alejandro. I think, how do you recommend to start in AI? I guess from my personal experience, it's always better not to directly jump to AI. Like the way I started all this, research, just start everything from Python, right? And most of my works are using Python, so that's why I really recommend you guys to participate in this Geohackathon and also in the Python tutorial. Python is very versatile algorithms, right? It's really good, especially for machine learning. So once you understand Python, once you know how to use Python, then you can start thinking about applying machine learning or using machine learning, right? Because at the end, it's not about AI per se, right? It's about your skills. Your skills in programming and using Python is much more important than your knowledge or skill in applying AI. Okay? Because even nowadays, some AI algorithms is already pre-built, right? So you can just click few, you do a few clicks and you get the results. But you don't understand what's actually going on. You don't understand how to build all this, right? So it's better to start with Python, take it step by step, just do it patiently. And once you familiarize yourself with Python, then you can start, doing some exercise using machine learning problems. Yeah. Guess any other questions, or that's pretty much all?
I wait if there is any other question. I think that could be all the questions that
Okay.
the public must have. And again, thanks a lot from the SCG Geophysics and SCG Economic for this talk. And I have totally recorded and made available in YouTube shortly, so that the people that couldn't assist can watch the meeting.
Okay, sure. So thank you. Thanks all for attending, and wish you a good day. Thank you. Bye.
Thank you, Jordi. Bye-bye.